So this session will talk about adding data to RMG. It's kind of like a supplement to the previous data um, presentations that I did earlier today. Okay, so important thing to note is that most parameters in an RMG model are estimated. Um, in an RMG model, you'll typically have thousands of species, if not, and perhaps tens of thousands of reactions that are under consideration at some point. Um, and so there's no way for us to conceivably calculate properties for all of those or have data for all of those. So often we rely on data-driven estimations to quickly predict those. We talked about how groups and trees do that previously. For thermo, especially, we look at group additivity, and kinetics, we look at decision trees. And so uh, so why you might want to add more data is that these estimators for predicting are fit to the data. So more data covering a bigger chemical spaces means better estimators. You might figure out through your sensitivity analysis also that you might have some sensitive reactions. So gathering data for those specific reactions could really help get more, better results. So a typical workflow might look something like this. Especially previously, um, you might want to generate data through quantum chemical calculations, and so this involves running those electronic structure calculations using quantum chemistry, using some sort of transition state theory or master equation calculations to go from those QM calculations into kinetic information, pass that on to RMG, and then do the simulation analysis as we saw earlier. Um, so what this talk, we'll talk about many of these tomorrow, including Arc and Arcane, and I believe RMS too. Um, so today, we'll talk about kind of like how to get data, go from this middle part, like that thermo and kinetic data, and put that into RMG specifically. By the end of today's session, you'll be able to describe RMG's data sources, add new species thermodata, add new training reactions, and sorry, this last point is not correct. We won't talk about running the RMG job with the updated RMG database, but you should be able to do that regardless. Um, okay, so here we've listed out all of the thermochemistry and kinetics data sources. Um, there's the libraries for both thermochemistry and kinetics, and those are compilations of experimental or computed data for specific species or reactions. Then we have thermo groups, which, as mentioned previously, rely on group additivity to just to linearly describe species thermochemistry based on the sum of its individual components. We briefly mentioned earlier that there is a thing called QMTP. That's basically an on-the-fly QM calculations that nobody really uses too much anymore, so we won't talk about it in this talk. And we also mentioned that we used to have an ML estimator that's not currently working for this version of RMG, but will perhaps be added in the future when ChemProp is updated. Um, we'll very briefly touch on that. And then, yeah, for kinetics, there's the libraries and there's families which are described through trees. So we'll go more in depth and explain more in this talk. Thermal libraries set thermochemistry for specific species. And here I'm just going to go through the anatomy of one of the files and the hopes that if you want to add a file yourself that's in the thermal libraries, you'd follow like kind of like this recipe. So at the top of each thermal library is the name of the library and optionally some descriptions, just to give the user some idea of what it is. And each of the after that, there'll be a list of entries. Each entry starts with this entry block. Um, each entry has a specific index, specific label, and then an adjacency list that describes the structure's graph structure. And then you can include the thermodynamic data through thermodata, NASA polynomial, or Will-Hoyt. And that's pretty much it for thermo libraries. It's pretty straightforward. If you want to find them, they're in RMG database /input/thermo/libraries. You can manually add them, Or if you have Chemkin information, you can use import Chemkin library Python script. Oops, sorry. Um, okay, and then more specifically, if you want to generalize to new molecules, you can define thermogroups. Um, Similar to before, there's a header with like the metadata, and then you have entries, and each entry has like index label. Um, then you have these adjacency lists that define the group. The one thing that's it's different here is that the adjacency list needs to have this asterisk to denote the atom that this group's applying thermochemistry to. Um, you also have to have the thermo in a thermodata format. So it's kind of similar to the library structure, but with this, it's maybe a little trickier to define the adjacency list for the groups and to define the atom. But otherwise, it's mostly the same. Um, for this one, it's in input thermo slash groups. Um, you will have to fit the groups values beforehand, like before you input the values in, um, and define the group structure kind of manually. Um, we normally have tools to help you visualize thermo groups. But again, from on the website, they're currently not working, but hopefully they'll be up soon. In the meantime, I believe they're working in native RMG, so you can use those. Um, Here's a list of the groups that we've defined so far, and the various files that have those different groups. There's group.py for base groups. We have the hydrogen bond increment corrections for the radicals, and we have all sorts of different ring corrections and Gauss 1,5 corrections, aromatic, and all sorts of just different miscellaneous corrections. Um, and certainly you're welcome to make your own if there's something else, some other sort of chemistry. Um, okay, so that's it for libraries and groups. QMTP, we're gonna skip over just because it's not really used. We're gonna jump to ML estimation for thermo. Um, move this out. Um, so for this, this is basically we've trained ML estimator to directly like predict thermal properties, but it's currently not in RMG for this latest version. And it's also not designed for users. To develop on, if you want to develop more on this, then please let us know and we can maybe work together. And also in general, we suggest using group additivity. ML estimation really is mainly used for a few systems. Um, so that's mainly it for thermochemistry. What we'll look at next is kinetics. So for kinetics, we have the libraries and the families. So libraries are defined also in a pretty straightforward way. There's a header, and then you have the entries. Um, as we mentioned before, instead of adjacency lists for each of the reactants, you'll have to define those separately in a dictionary, which has the adjacency lists. And then for the kinetics data, you can include any of the following of Arrhenius, multi-Arrhenius, P-dep Arrhenius, multi-P-dep Arrhenius, Chebyshev, third body, Lindemann, or Tro. Um, Here's what a dictionary file looks like, where each of the names of the species are listed, and then you have their adjacency lists under each of them. And everything has to like be consistent. So these are listed in RMG database input kinetics libraries. Um, in order to these are that they have that Python syntax file and the dictionary file. And in order to add to this, you have to manually add new files or entries following those templates that I showed earlier, or use the import Chemkin library script. So yeah, in general, I'd say like libraries aren't too complicated. And um, one, well, I'll describe later the difference between library and training data. Um, Actually, I'll get to that later. Um, the next thing is kinetics families. Um, Kinetics families are formatted like this, where you have the header. And in addition to the other files, there's also a recipe and a template. The template specifies the groups, and the recipe specifies like the um, bonding edge and, for example, if radicals are gained or lost. in according to the reaction. Um, you'll see that in the entries, the important atoms corresponding to those recipe actions are labeled. So for example, you have a star one and a star two corresponding to change bond. And in this first entry here, you can see that there's a star one, star two corresponding to which of those groups are having their species or atoms modified. Another thing to note is that you have groups for each of those individual reactants. So for example, this entry is R underscore R, but the complementary reactant is YJ2. So there's gonna have entries that are also that species in the same file. You also have to specify rules. Rules give you um, the rates for like a pair of reactants. Um, So each entry here is just each individual entry is just a rule for those pairs. Um, again it's mostly the same here. You have like a header and you have entries with each of those entry blocks, and um, you can provide the rate parameters. Okay, so these are a little bit more complicated. You need to provide the groups file that defines what each of those individual nodes are. You have to provide a rules file that provides the kinetic values for coordinates of pairs of those groups. And then we also have something called training data that I'll describe in the coming slides. Um, uh, in general, we used to fit these fill out a lot of rules manually. But we shifted more to using training reactions instead to populate the rate rules. Which and I'll describe what that actually is. Um, Training reactions are used to automatically generate the rate rules from a set of uh, library data. They're base. If you look in the RMG database, you'll see like there's the libraries, but then separately there's also the training data. They look very similar, but the training data, um, will have reacting sites labeled properly based on the recipe. Um, sorry. Um, they'll have different labeling of the atoms, and so which is very tedious for the libraries. So we instead do that automatically with the Jupyter Notebook. Um, um, so basically, all you need to do is have your library data, and the notebook will automatically go from that data and label the reacting sites according to the recipe of the family and fill out the rate rules according to that. Um, yeah. So if you want to do training reactions to automatically fill out the family values, then you have to fill those out in the ARMS database, input kinetics families, family name slash training folder. And those include Python syntax fractions file and an ARMG style species dictionary. And I'll show what this looks like shortly. Okay, so that's the end of this presentation. I'll show like some scripts that are helpful and maybe illustrate this a little bit more. Um, Here is the GitHub page. Um, all I'm showing here is that uh, all I wanted to show here is that if your kinetics family is not auto-generated, then it'll automatically add rules from training when you load your database. Um, so that's where the training data is fit to the trees. Um, if you want to go from a kinetics library to training reactions, which are then automatically used to fit the trees when you load the database, you can use a script called kinetics library to training, which was previously shown in this slide. Um, it basically will load the library, take a specific family to add training reactions to, and find matches from that library to that family and add it to the training data. So if you want to run this notebook, it's in the data. Let me see. I forgot if it's in the database or the Python scripts folder. It's in one of them, and you can just run this. Um, Sorry. Step one is just loading the database, so you can just load it. Step, oh yes, I can make it bigger. Step two is to generate the library reactions that match the family template. And so this is just a big table that includes all the matches from uh, from the library. And you can see that this is showing like the orange is the old estimate of the kinetics for that reaction, and the blue is like the data's kinetics. And you can see that actually there can be quite a big difference, and so it's important that in this case we were adding the new data. I'm gonna scroll down more. Okay. So then step two is to be optional is to review and select reactions to be added, because in general we want to be very careful about which reactions we're adding to the data. Um, what this will do is it will prompt you to review all of the reactions that will be added to training, and you can either say yes, you want to add it, or no, you don't want to add it, and so on. So I'm just going to say yes for a few of them just for demonstration purposes. So you can do this before just to decide which reactions to add from the library to go into training. Um, this will this step 2C is just to see if there's any manual multiple matches or not. There wasn't any. And then in 2D, this will basically go through final review of reactions. It'll basically do what was shown earlier, but not prompt you. It'll just show you everything that was added that will be added to the training. And finally, step three will write the training reactions to the database. So you just run this, and it will add the reactions from this library to the intra-R add endocyclic family. And previous repository had 852, now we're adding 27. Um, so that's just an example that you can do. What this might look like in practice is you might run your QM calculations. You might go through Arcane and then convert those calculations into kinetic library data, for example, and then add that to uh, its own like a new library that you custom define and go from that library to training data. And that will improve estimates for everybody who uses RMG data if you commit it and upload it back to the RMG database, which Jackson will talk about in the next session for how to do stuff like that, I believe. Um, some other stuff to note for kinetics estimation, if there's multiple training data that fall into the same node, there's a priority system for which data to use. In general, experiments are the most, or yeah, experiments are the most trusted, followed by some very high accuracy QM calculations, and yeah, and so on. Um, Let me see, a few other scripts that might be helpful. If you want to um, fit a tree automatically rather than generate it manually, you can use this BM tree fitting notebook that will do that. We're not going to go through it right now, but just
Flowers Maisel.
yeah, Blatters Mazel. Um, I'm not going to go through it right now. There's also a script called fit thermo groups from thermo library, where you can go from thermo libraries um, and fit thermo groups, kind of in a somewhat automatic process. I won't go through it because this is also very long. But yeah. And then this is the import chemkin library script. If you have a chemkin file, um, it will save it to kinetics and thermo library files automatically, doing that conversion for you. And this is an RMG database slash scripts. Let me see. Okay, so those are just some of the scripts and ways that you can add data to the RMG database. If anyone has any questions, please let me know.
I think you've said it a couple times, but can you remind what's the difference between a library and a family?
Yeah, so a library is kind of just like a data source, where you have specific reactions or like molecules with specific values, like their action, like Yeah, it's just for like a specific reaction. But a family encompasses a broad like class of reactions of a certain type.
And
Like
we can use a library to fit a family.
you can use training data from the library to fit um, nodes of the tree for the family. Yes. There's a slight distinction between library and training data. So I didn't make this distinction, but for some reason, how we do it is that like we have a separate library repository and we have a separate training data repository. And only the training data is used to update the values, fit the values automatically. The reason it's separate is you might want to have specific values for specific reactions that don't go and affect the trees, especially if they're like unusual or weird types of reactions, for example, or like the rates are kind of like really different. So for that reason, we keep that distinction and don't automatically put all of the library data into training. Does that make sense?
Yeah, that makes sense.
Yeah, I think that was very clear. The families will predict new chemistry they've never seen before, right? You give a totally new molecule that someone just invented, and the families will be able to say, oh, there's an H, I can abstract it using H abstraction. Whereas a library is like, if you haven't seen that reaction before, like you're not, so the library, you only the reactions that are in the library will ever show up. Whereas if it's in a family, it will extrapolate to make up new chemistry.
Does this exist? Who keep it?
Which bit? The fitting, the tree generation,
Yeah, the regeneration.
so the automated tree generation where it decides the structures itself was Matt Johnson and was 5-8 years ago. But we haven't converted all of the families over to that format yet. You showed us clearly how to make the training data for from a library, but then the script that you kind of mentioned but didn't go through is needed if a family has already been turned into the new trees, the blower's muzzle, then getting the stuff into training data is not enough. You would need to refit the blower's muzzle trees, right? So.
Great.
So, yeah, one more thing to anyone out there in the community who's like, oh my God, that's hard, I won't bother. Please reach out for help, right? We would rather help people add data to the database than not have people add data to the database, right? So it might be too hard to do it on your own. That doesn't mean don't do it. It means ask for help because we want your data.
And we're also looking at potentially making improvements to the RMG database, and we don't have plans. So may want to move to different formats too. So if you have ideas for how to do that, or would like to contribute to that, especially, please reach out to us because we'd be very excited to do that.